Greetings once again. Resonance is one of those fun topics that you run into when you look at wave phenomena. And one of the subsets of resonance is related to the phenomena of standing waves. This video was going to look at standing waves. So just as a quick review, standing waves are generated when you have two waves moving in the opposite direction in the same medium that's superimposed under just the right conditions. What are those conditions? Well, to begin with, we're assuming that there's a periodic force that's being applied to the medium that's generating the wave. We're assuming that that wave bounces off the end of the medium and generates a return wave. And we're assuming that the frequency of the driving force that produces this generated wave matches one of the natural oscillatory frequencies of the system. If we get all those conditions, the generated wave and the bounced wave will superimpose in a very orderly way, and it will produce what's called a standing wave. So here's just a little schematic. Here we could have, like, say, for instance, a string. It's fixed at one end. You grab the other end, which is going to act like a fixed end, but you're going to jiggle it just a very little bit. That's going to generate a wave. That wave is going to move down. It's going to bounce off this end and come back in this direction, so you have the bounced wave moving this way. But because the jiggle continues, you have the original wave continuing, and so you end up with two waves that are moving in the opposite direction on the same medium, and they will superimpose in a very orderly way if the frequency of this force matches up with one of the natural frequencies of that string system. And what that means will become evident here shortly, if you don't already know. So let's say that the frequency of the force function that was generating the wave in this system happened to match up with one of the natural frequencies that the system could oscillate at. Under that circumstance, what might a standing wave end up looking like? Well, what you're about to see is a very stilted, sort of slow motion version of what that motion might look like. Of course, what you just saw was not to speed. If you had something that was oscillating at 5 or 10 or 15 cycles per second, it would be just a big blur, and the standing waves would just kind of would generally, the outline would show itself as what you're seeing here. What's important is that there are particular areas on the standing wave that have been given names because they're significant. One is areas where there's no motion at all. The superposition is such that the net sum of the two waves, the wave going this way and the wave going this way, always adds to zero, and so there's no motion. These are called nodes. And then there are areas where there's an enormous amount of motion, the maximum amount of motion that the string, in this case, could execute, and those are associated with what are called antinodes. So with that background, it's time to take a shot at a problem. So what we have here is a steel bar that is constrained at the center. It's like it's pinched at the center. It's held at the center. The speed of sound in a bar is about 6,000 meters per second. I'm going to assume that the bar is 2 meters long. And the question is, what's the second lowest frequency that can resonate on this structure? And this is basically a standing wave problem. So as is the case with all standing wave problems, the first thing we need to do is to determine the possible waveforms that conform to the endpoint constraints of the system. And we need to talk a little bit about what that means here, and we will do that shortly. Once we have an idea of what the waveforms are going to look like, we're going to pick the one waveform that fits the criteria for our particular problem, then determine what its wavelength is in terms of L, where L is the overall length of the system. I realize this is sounding kind of formidable at this point. Don't worry about it. You're going to see all of this happening in action relative to this problem in a couple of seconds here, and you're going to realize, you're going to see it's not that awful. So finally, we have this relationship that relates the wave velocity to the wave length and the frequency. We know what the wave velocity is of sound in steel because we were given that in the problem, the original problem. We know what the wave length is for the waveform that's going to do the job for us because we just figured that out in terms of L. And so all we have to do is figure out what the frequency is. So how does all of this work within the context of our problem? Okay, so beginning with the endpoint constraints. This end can flop around, which means it will have an antinode associated with its motion. So the left endpoint constraint is an antinode. The right endpoint constraint is also an antinode. It can flop around also. We will additionally have a node at the center because we've actually pinched the center. So now that we know what the endpoint constraints are, we need to match this up with a waveform. So we start off with a sine wave. And we find an antinode because we know one of the ends of the system has to be an antinode. And we move until we find another antinode. And we say to ourselves, will this work? If the length of the bar were such that there was an antinode here and an antinode here, are all of the constraints met? Well, the endpoint constraints would be met. But it turns out we also have to have a node at the center. And if in fact this happened to be the wavelength we were dealing with, lo and behold, we would have a node at the center. So apparently this particular wavelength could stand on this structure successfully. And in fact, if it were to do that, if we were to do that, we would end up with oscillations that look like this. Additionally, if this had done the job, we could pretty easily figure out what lambda was. Here is one wavelength in terms of L. You can see there are actually two L's in lambda. Turns out there's a much easier way that will always work to figure out the relationship between the wavelength and L. But in this particular case, you can just see what the relationship is. Now the problem with picking this particular waveform is that it's associated with the longest wavelength and hence the lowest frequency that could stand on this structure. We want the second lowest frequency. So what we're going to do is we're going to keep this endpoint constraint, and instead of using this antinode, we're going to go out to this antinode and we're going to see whether or not that would work. And so here we have it. Left endpoint constraint is an antinode. Right endpoint constraint is an antinode. The problem here is that there's no node at the center. This particular wavelength would require the center to be able to flop around, and in fact, we want it to be able to be pinched. So this particular wavelength isn't going to do the job. So we go out to the next antinode. So what do we now have? Well, we've got an antinode here. We have an antinode here, so our endpoint constraints are matched up. And lo and behold, in the center, we have a node. So apparently this particular waveform, this wavelength, whatever it is a wavelength that can stand on this bar, given that the bar is constrained in the center. And in fact, this corresponds to the second longest wavelength or the second lowest frequency that can resonate on this bar. And if in fact you were wondering what this thing would look like if it was actually oscillating away merrily, I just happen to have an animation for you. So that's what it looks like, and you don't really need to know what it looks like to be able to do the problem, but I thought I'd throw it in. In any case, to do the problem proper, the next question is, how do you relate lambda to L? So back a ways, I said that there was this clever way that you could go about doing this that was pretty easy, and this is it. the question that you ask is, how many quarter wavelengths are there in L? Or in mathematical terms, how many quarter wavelengths are there in L? So we look at the sketch. There is one quarter wavelength. Here is a second quarter wavelength, a third, a fourth, a fifth, a sixth. There are apparently 6 quarter wavelengths in L. So if we reproduce our relationship and we put in the fact that there are 6 quarter wavelengths in our standing wave, and we additionally identify L as being 2 meters long, which is what it was defined as in the problem, we can determine that the second longest wavelength that will stand in the system is going to be 1.33 meters long. So now we know what the wave velocity is. That was 6,000 meters per second. We know what lambda is because we knew what L was, and we were able to come up with a numerical value for lambda, and from that we can figure out what the frequency is. And if we just do the math, lo and behold, apparently it comes out to be 4,500 hertz. So this is kind of an exotic standing waves problem because you're looking at a structure that you wouldn't normally tend to associate with vibration, although you guys do know that if you take a piece of metal and you strike it, it will ring. And what you're hearing with that ringing is the resonance. There is a frequency that structure is vibrating at. That's why you hear it ringing. Anyway, that's it.